Okay, hello AP Chem students. What we're going to talk about is an example of sulfuric acid that is a diprotic acid because remember sulfuric acid is H2SO4. And what's unique about sulfuric acid is it's actually classified as a strong acid. And it's a strong acid because only the first protonation of sulfuric acid is strong. So if you are thinking about what sulfuric acid looks like, we think of it as H2SO4. So there's my H2SO4. Well, this protonation, so just releasing that first hydrogen ion is strong. And when we look at that and we were to write that equation, H2SO4, notice the arrow is only going one way because that's almost nearly to completion, that almost all of the hydrogen ions will completely dissociate. So calculating the concentration of the hydrogen ion for the first protonation of sulfuric acid is very easy because it is a strong acid. The concentration, as you'll notice, is the same as the original concentration of the acid that you were given in the problem. What do you see in the beaker then as far as major species? You have a lot of hydrogen ion, as we have right here. You have the HSO4 ion, and you would have water in your beaker. The second protonation, so now that means the protonation of the HSO4 ion, when we look at that, that will exist in equilibrium because it is a weak acid. So notice the double arrows for the weak acid. So you will have to calculate both hydrogen ion concentrations. You got to calculate the hydrogen ion concentration from you really already did it from the first protonation. It's the same as the concentration of the acid. And you will also have to calculate that hydrogen ion, the second protonation. And as you know, since it's a weak acid in the second protonation, you have to use rice tables. So when I build my rice table for that reaction, here's the equation, HSO4 going to H plus and SO4 2 minus. When I build that reaction, you will notice that I have some initial concentrations. The initial concentration of the HSO4 is 0.01 molar, and that is coming specifically, that's coming specifically right from here. So that concentration right there, that is where that is coming from. It's 0.101. What is the concentration of the hydrogen ion? Well, because of that first protonation, it's right here too. And you have 0 sulfate ions yet because we haven't allowed for that second protonation to happen. But when we do, we know we're building an ice table. So there is going to be a change, and you are going to add a little bit more hydrogen. You're going to add some sulfate ion, and you're going to consume some of the HSO4 minus, and that's why there is a negative X there. So the equilibrium line ends up being this 1.0 or 0.01 minus X. Notice the hydrogen ion is 0.01 plus X. So really, when you think about it, this is representing right here the original hydrogen ion concentration from the first protonation. This represents the hydrogen ion concentration from the second protonation. And then, of course, X would represent the amount of sulfate ion that also is formed. So when I place this, and I'm going to do this Ka, and where did I get this Ka value? Okay, well, they would give it to you on an AP exam. Here we go. They wouldn't expect you to memorize that Ka value. They would give that to you. You would have a chart, as we know, and you could look it up. Actually, the Ka for the second protonation is 1.2 times 10 to the negative 2. Now, in all of the videos that I've been giving you, we've been talking about how you can ignore X. However, this is a place where you should be cautious. And the reason why you need to be cautious is that look at this initial concentration of 1.0 times 10 to the negative 2, which is the same as 0.010. look at this Ka value right here. The Ka value is very close to the concentration of the acid that you have. So what happens is that you can't say that you can ignore X. You can't say that X is 1.2 times 10 to the negative 2, and that's equal to the hydrogen ion concentration because it's larger than 0.01, which, this 5% rule doesn't work. So what you need to do is, in this case, you would need to solve using a quadratic equation. Okay, and here's my example. I've just kind of made these things smaller so you can see the work that we have here isn't anything new. You can see I built my rice table and it's right there in the upper right hand corner. To do the quadratic equation, okay, and you guys, I know you probably have solvers, you can graph it, you can do it by hand the old way, whatever the case may be, but I want to alert you to a couple things. Now, this is the K expression, and I just copied this right directly from the book because it was easier to do a screenshot than type all of this stuff on into my notebook here. But now this is representing the equilibrium expression, and the Ka is 1.2 times 10 to the negative 2. Notice this is this equilibrium line that I'm substituting in here, okay? So we can't ignore X in this case. And when we solve, it leads to doing algebra and setting all terms to 0, which you should do with the quadratic equation. And what happens is that the quadratic equation, if you don't know the song, here's the equation so that you can remember it, where A is equal to the 1, B is equal to 2.2 times 10 to the negative 2, and C is equal to negative 1.2 times 10 to the negative 4th. And just to kind of remind you guys, we got those terms. So this is the A, the B, and the C part, okay? So when we solve this, and again, I don't need to see you solving the quadratic equation, nor does AP Chemistry. If you do have to solve with a quadratic equation, I do want to see all terms set to 0. And then what's going to happen is that if you remember, you get, let me see if I can, let's see. If you would remember, let's see if I can get this moved back up where it should be. There we go. If you remember X, let's go back to X, you will have two values of X when you get a quadratic equation, okay? One of them will make sense and one of them won't. As what they're saying here in the textbook, when you do this, use the quadratic equation gives one negative root, which cannot be correct because you can't have a negative X. Because if you have a negative X or any concentration that is negative, that doesn't make sense. And where you can't have a negative root is if you look at the sulfate concentration, right? If X was negative, you would have a negative sulfate concentration. What does that mean? That can't be possible. So if that is the case, what I want you to do is show your two values of X, and you're going to end up crossing one of them out, circling the one that is correct. In this case, as the book says, you're going to use the positive root, which gives you this value right here. So that's the one that you should have circled. And then, let me just get that moved over. And then you can solve for the hydrogen ion concentration. So the hydrogen ion concentration is 0.100 plus X. And so notice what's interesting about this is that that concentration is pretty high. It's almost half the amount of hydrogen ion is being dissociated from the second protonation compared to the first protonation. So that's a pretty significant amount. And then they went and they solved for the pH. What I would want to see in this case, let me go to black here. What I would want to see is I'd want to see that pH, really struggling here today. What I would want to see is pH is equal to the negative log of 0.145. as we had shown in those other videos. You know what I'm saying is show the equation, show the substitution, and please show better handwriting than this. Really struggling with my iPad today. Okay, I hope this helps, and good luck.